All right, back to the drawing board, quote unquote. We're on homework 3 for Thermodynamics II at South Dakota School of Mines and Technology. This is the homework on partial molar properties, which is a mixture of calculations and graph stuff. So number 2 is another calculation problem. So it says, consider an ideal gas mixture at this pressure and this temperature. It contains this many moles of species A, this many moles of species B, and this many moles of species C. I can plug those in to find out what X1, X2, and X3 is. Okay, but basically, I have 3 components. Okay, and I'm asking for all these different things like V1, V2, partial molar V1, partial molar V2. I guess I'm not asking for anything in component 3, which is weird, but whatever. Okay. Now, this one is unique in that, hey, it's an ideal gas, okay? And the reason I give this problem is to show you, well, ideal gases act like ideal solutions, okay? And that things like we talked about in class, how ideal solutions would add completely, they would be additive. Like, I add 50 to 50, I get 100. Okay, I don't get this goofy math, 50 plus 50 gets 97. Because when I do that, it's because I have a mixing term. In this case, I'm essentially going to have no mixing term. I'm just going to ideally mix. Okay, so it's a good practice in approaching the math. Okay, so if I look at this, B is equal to RT over P. Okay, straight up, no questions asked. We know that as fact. Okay, for ideal gases, and it doesn't matter what's in there. That's what it is. Now, why doesn't it matter what's in there? You may be like, oh well, why doesn't it matter what's in there? Well, by definition, an ideal gas says there's no interactions, and so it doesn't matter if I have nitrogen and oxygen or whatever, like A, B, and C, because there's no interactions. Then A is oblivious to any B that's in the room. Same thing with the C. And so this is just the way it is. Okay. But I would approach this the same way I would approach everything. And so, okay. And so, how do I get V1? Okay. Well, V1, by definition, if I read that, it says the volume of component 1 as a pure system. Okay? And what does that mean by pure system? That means that x1 is equal to 1. And if x1 is equal to 1, what is x2 equal to? That's right, it's equal to 0. Okay? And what is x3 equal to? Last time I checked, 100% has to be 100%, so x3 has to equal also equal. And you might be like, well, Dr. Hadley, there is no x's in there. Hence why this is unique. I still plug it in. V1 is equal to RT over P. That's it. It's done. I've done what I had to do. And guess what V2 is going to be equal to? Well, V2 is when I have x2 equals 1, and meaning everything else goes to 0. X1 goes to 0, and x3 goes to 0. And oh wait, hey, that also equals RT over P. So, and guess what V3 would be if I asked it? That's right, RT over P. Okay. And to actually calculate it, I just plug in some numbers. Okay. So, now, partial molar. Okay, let's do partial molar. Now, there's 2 approaches when calculating partial molar properties. Okay, it can either go by the binary thing from Smith and Van Assen and Abbott, or I can do from the definition. Is this system binary? Not quite, so I have to use the definition. I cannot use the binary stuff if it's not actually binary. Okay, so that is the biggest thing. Now you might be like, okay, well, I'll just do everything from the definition. that's fine. But sometimes the math is easier if I go binary, okay? If it truly is a binary system, not usually, but sometimes, it really depends upon the situation, but, I'll try and hint at which one would be better, okay? But in this case, I have to, there's no choice I have. Okay, so how do I approach this problem, okay? So first off, I recognize it as a partial molar property problem, okay? Obviously, because there's a big bar over the V1, so that's definitive, okay? Number two, I write down the definition. So partial molar V1 is equal to d capital V dni, or dn1, at a constant t, p, n, j not equal to 1. And you're like, okay, Dr. Hadley, do I really need all? Yes. You need everything. Because if this is not constant t, p, n, j not equal to 1, then it is not a partial molar property. That is, by definition, as we derived in class, as derived by thermodynamics, as derived by whatever, okay? This is its definition. And even if I look at it from a numeracy point of view, it matches the actual definition of what partial molar properties are, okay? So I have to have the Tp, okay, and the Nj not equal to 1. I have to. I have to. I have to. Now, okay, so I have little v equals RT over P. How do I get from a little v to a capital V? Alright, I multiply by the total moles. Okay. Now, because remember, this is a capital V, and I can't just, what is D and I? Oh, that must be 0. No, I have to use capital V. I have to use capital V. I have to use capital V. Okay. And how do I get capital V? Well, I have to multiply by total. And then my little v becomes a capital V, and this is equal to NT RT over P. And that's our classic, PIV note. Okay. And that's what everybody loves. Okay. So, now that I have a capital V, now I just take the derivative. Okay. But I cannot forget that NT, well, I can't forget that, but look at what it says. Nj not equal to 1 is constant. Does it say total moles? No. And so if I take, because there's no n1s in here, right? So if I take the derivative of this, it should go to 0, right? I got to think about what the math says. If I take out the oxygen in this room, aside from me passing out, am I changing the total moles of gas? Dang right I am. Okay, so NT is changing. Now, are RT or P changing? Well, is R a constant? I would hope so, because it's called gas constant. Is T constant? Is T constant when I change the moles of something? Doesn't matter. That says it's constant, and that says P is constant. So, I don't care if T can change with changing moles. I don't care if P can change with changing moles. Doesn't matter, because I've told you that it's constant. Okay, so I have to assume those are constants also. Okay? And so, when I'm doing this, usually what I want to do is, use a chain rule so that really dV, dN1, dP, and J not equal to I1 is actually, and I'm just going to shorthand it, dV dN total times dN total dN1, okay, with all the same constants. You don't have to show it that way, but just remember, be keeping that in mind. Okay. So, partial molar V1 is equal to, well, what is dNT dN1 equal to? That's equal to 1. Okay. Because if NT plus NT is equal to N1 plus N2 plus N3. Okay. So if I look at this, okay, what's the derivative of this guy with respect to this guy? 1. Okay. What's the derivative of this guy with respect to what's the derivative of this guy with respect to N1? What's dN2 dN1? Should be 0 because everything else is kept constant. So that's constant. That's constant. And so what I'm left with is 1. Okay. And so, okay, well, and dV dNT keeping everything else constant is RT over P times 1 is, well, RT over P. And then so I take the derivative, okay, and then I clean up the math. I turn all my moles into mole fractions, but I don't have any moles or mole fractions. And then I clean it up. Well, it's already as cleaned up as it's possibly going to be. Okay, and then I put a big bow on it and say, hey, I'm done. Okay, and well, I'm done. You're like, well, Dr. Hadley, that is what you started with. Well, you also remember I said this is an ideal gas, and I defined how ideal gases behave. So if I look at the words, how component 1 contributes to the total volume. Well, if nothing sees anything else, it's like ideal gases are the biggest megalomaniacs in the world. They think they're the only things in the universe. So I am the volume, this one particle, or species 1. Okay, by definition. And I get the same exact thing with V2, partial mole of V2, and so what would be the point of re-deriving it? It wouldn't. Okay, and V, well, I already know what V is. Okay, delta V mix. All right, so, let's hear. Delta V mix is equal to V minus V ideal solution. And V ideal solution is equal to summation of Xi Vi. Well, this one is RT over P, already established that, minus X1, RT over P, minus X2, RT over P, minus X3, RT over P. Well, what's X1 plus X2 plus X3? 1. Okay, so that's RT over P minus RT over P, which is 0. Meaning, well, an ideal gas is an ideal solution. Okay. So, now, what about capital V1? Well, I know what little v1 is. So capital V1 is equal to the moles of N1 times the molar volume of component 1 as a pure system. Okay? And so that's where I would add that. And same thing with V2 in terms of V, well, that's just the total moles. Okay, so nothing crazy. It's just to show you how this math works on an ideal gas, to show you that ideal gases are ideal solutions. And that it doesn't, there is no contribution, quote unquote, of component 1. Or rather, its contribution is everything. It is the mixture. Okay?